Good morning, everyone. Good afternoon, everyone. My name is Aubrey Pomorsi, and I'm the project manager with Jake Engineering. And with me today, I have Jonathan Bone, our water resources engineer, Emil Fries-Villen, our structural engineer 1, Lindsay Khan, our transportation engineer, and I am structural engineer 2. We'll be working on the East Gate redevelopment and designing 2 buildings and a road and a parking lot to go onto this area, which you will hear more about when I pass it on to Kenzie Khan.
Thank you, Aubrey. As Aubrey said, I am the transportation engineer for Jake Engineering, and I have been tasked with a roadway between Sturdy and Silhavy Road, and then an improvement of the intersections. In addition, pedestrian facilities will be improved, and there will be a parking lot for the 2 new proposed buildings. So this is my detour route for the project. I did pick a truck detour and a main detour just because this curve right here would be too tight for trucks to turn around. So I picked it's only a few minutes different though. So, and as you can see, Sturdy Road will only be closed because of the intersection that we will be improved right here, rather than this one is just a one-way stop. So that will not need closed down. So as you can see, this is my new road alignment. There is lighting, roadway signs, in addition to speed limit signs. For that, the pavement parking will be included, just for roadway to keep the maintenance, right? And then in addition to that, there will be a 5-foot sidewalk south of the road, and then 500-foot curb radius. Right, yeah. And then this is the typical section for the roadway. As you can see, there will be a 2% typical slope, and then a 2-foot buffer on each side of the road with a 5-foot concrete sidewalk south of the road. In addition, there will be 2 ditches on the each side of the road. And then from down here, you can see that there'll be a local road and a collector road with 3 layers each that contains aggregate, base and surface, which would be the typical section of the pavement, and then for the parking lot, it will just be base and surface. So here is the parking lot layout. As you can see, there will be 217 20x9 parking spots with 5 20x9 handicap parking spots with 20x5 access aisles, and then in addition to 2 20x11 van parking spots with 20x5 access aisles, and then 2 bike racks and 1 loading zone. This is all in accordance with the ADA and then the parking ordinance of City of Valparaiso. And then here's a more in-depth dimensions of each roadway, in addition to radii of 20 feet for the curve and the entrance, and then 10 feet for the entrance into. So this is the Sturdy Road intersection. As you can see, there will be 30-foot radii for each corner, and then the 8-foot crosswalk for each road, and then a connection to the concrete sidewalks. And then addition to that, there will be 12-foot lanes for the new roadway, and then the existing roadway is 15 feet just because it was already designed, and then it will be a level of service B with a delay time of 13.1 seconds. And then here is the Silhavy Road intersection. It is a one-way stop, or a one-way stop. And then in addition, this will continually travel. And then I added an additional crosswalk across the road just to give connection to the existing sidewalk that's over by like the Menards area, and it'll have a connection to that. So if people want to travel through here, they can get through that through walking distance. In addition to that, there will be a 60-foot curve radius in order to the entrance, and then a 30-foot curve radius for the exit. And then this is my cost estimate. As you can see, it includes the aggregate, or the aggregate surface base for the pavement, and then it includes the sidewalk, bike racks, pavement markings, lighting, signage, and then other than that, it is about a little over $1 million. And then for that with demo, it's about $2.2 million. And now you'll hear from our first structural engineer, Emil.
Thank you. As one of the structural engineers, my responsibility has been designing a retail and residential building. With this being the last presentation, I wanted to go over the major design components and kind of see how we ended up with the final design. The retail and residential building is kind of an attempt to revitalize and bring new life to Eastgate. It's going to be in close proximity to a VU academic building as well, which is kind of to try and integrate the two communities, being the campus community and the city of Valpo. The one-story steel structure layout is very intentional and was decided upon earlier in the process, and took in factors such as environmental friendliness, accessibility, and cost. We use RISA a lot in the design process. Our first step was kind of build a model of the roof framing plan in RISA floor. Here we apply the loads as you see them here, all the vertical loads onto it. The most prominent is the snow load of 22 pounds per square foot. And when running this through LRFD load combination, it is has the highest output when going through load combination 3. And as you can see from our model and through the applied loading, RISA is able to go in and select members for us, so we don't have to do all this by hand. For the horizontal loadings, we use RISA 3D. We were able to take the same model and kind of throw it into RISA 3D with the same vertical loads, and now also apply wind load and seismic loading. This allows us to start designing for the columns as well as the braces throughout the structure. The braces are kind of done through like a trial and error process of placing braces throughout the frame until RISA tells us that it's stable. We also want to check for horizontal drift of the structure. We want to keep this below 0.36 inches, which is based on ASCE specifications, and is also a factor of the height of the building. Since RISA is designing a lot of these components for us, we of course want to check that RISA is running the analysis correctly. Therefore, we check various members throughout the structure to see if the members that RISA select can actually carry the applied load. The connections are done by hand. Here we looked at 2 bolt shear connections as well as tension member connections for the braced members. We designed typical connections for the entire building using the maximum applied load. This way we would assure that the design connection could actually be sufficient throughout the entire structure. We use the same approach when designing for the tension member connection, using the maximum tensile force in the brace members. As you can see up here, some of the members will need to be coped at the top because we want to maintain a flat roof surface from where we can place the roof deck, which is a 22 gauge metal deck spanning a maximum of 7 feet. For the concrete floor slab, we're designing a slab on grade. We do so using 3 different load scenarios for occupational use. We have retail and storage spaces and residential spaces. Even though we're designing a slab on grade, we want to account for soil erosion. Therefore, we're designing for a span of up to 3 feet. We're designing a one-way slab and providing reinforcement in both directions because we don't know which way the soil is going to erode. So we want to account for bending in both directions. The controlling steel ended up being the shrinkage and temperature steel for all 3 load scenarios. This means we have the same slab throughout the entire structure. The final design is a 7-inch thick slab using number 4 bars spaced 4 inches on center. My design also includes a covered outdoor space. This will be for the residents of the senior living spaces within the building. It's going to be a timber constructed patio structure. The main issue here was looking at a uplifting load from the wind. Since this is higher than the actual weight of the structure itself, it's advised that the building will be anchored down as not to be teared out of the ground. For the cost estimate, this time we used a line item estimator. Previously, we used a square foot estimator, which incorporates like every single aspect of a finished design building, whereas now we can go in and look at specific items we actually designed for in the design process. This also accounts for the labor hours needed for each item and comes out to a cost just below $1 million, or about $942,000. And I'll pass it on to John.
as the water resources engineer, I've been tasked with creating a stormwater management system that will reduce the negative impact caused by the additional runoff in the Eastgate property. So my design will improve the water quality by reducing the concentrations of suspended solids and nitrogen. And the design will also prevent flooding by temporarily storing the water volume correlated to the 100-year, 24-hour storm event. So here's the overview of my design. So as you can see, various kinds of stormwater treatment practices are used to capture and treat the water flowing in each runoff path. For example, anything flowing north off of the road will be collected by vegetated swales and transported to a rain garden to the east, where it'll be treated. Here's the primary development area where the majority of the impervious area is going to be constructed. So to the north, I have an infiltration trench. And then here is my integrated rain garden, which is built into the courtyard of the east building. So that will handle all of the runoff that lands on the roof. And then water flowing off of the site anywhere else will be collected by this vegetated swale and eventually transported to the east to be treated there. As you can see, there's also a dry detention basin here and a culvert. So here you can see the dimensions of my dry detention basin. So this was designed using level pool routing. To the right, you can see this figure displays the inflow and the outflow of the basin. So what the detention basin is doing is taking all that inflow that came in right away and just releasing it over an extended period of time. You can also see that the maximum outflow rate is always under the allowable release rate set by the city of Valparaiso. So here are my drawings for the detention basin. The outflow structure utilizes two Hickenbottom intakes, which are featured to the right. That outflow structure will allow water to flow through more of those little openings as the water level increases. So this just helps you control the outflow a little bit more. Here is are the dimensions and the design of my infiltration trench. So the trench will be filled with gravel, which will allow the water to quickly fill in the gravel and then slowly infiltrate through the existing ground. There's a perforated PVC pipe, which will relay excess stormwater downstream, which will eventually lead to those vegetated swales and to another rain garden separately. Here is the design of my rain garden. So each rain garden will be following this design. So there will be vegetation growing out of the mulch layer. And then since nitrogen is my targeted pollutant, I also use this modified outflow pipe, which will retain water in that anoxic zone, which will allow the denitrification process to be completed. So as a lower limit, the amount of water stored in this anoxic zone is at least equal to 1/2 of the water quality volume to ensure that 50% of the nitrogen is removed. Here are the other dimensions for my other two rain gardens. Here are my swales. So as you can see, the south swale is significantly larger than the north swale, and this is due to it receiving flow from the majority of the impervious area on the site. So this can be seen further in this diagram. So then these will also be lined with vegetation, which will help to filter out some of the larger solids and act as pre-treatment towards the rain gardens downstream. Additionally, there will be some infiltration through the bottom of these swales as it flows to the rain gardens. For the culverts, I decided to go with a 1.5 foot diameter concrete pipe. In the HY8 model to the right, you can see that the culvert is able to successfully pass the flow without flooding the road above it. Now, for the construction cost estimate, I estimated my cost using existing cost data for each specific management practice. So in total, it came out to roughly $763,000. So from there, I will pass it on to our second structural engineer, Aubrey.
Thank you, John. Hello, everyone. I am the second structural engineer with Jake Engineering. My goal was to design a 25,000 square foot academic building with 1,000 square feet of this building reserved for lobby area, which will be in the front of the building right when you walk in. And this building will be a one-story steel structure located where the red rectangle is on the screen, just as a little recap. As for my loading, a lot of the loads and the applicable loads is the same as, sorry, from last presentation. However, I did add insulation, ceiling tile, and waterproofing. And for my RESA 3D inputs, I use the ASCE 716 hazard tool and checked all of those values using the ASCE 716 manual with hand calculations. And these were the inputs into RESA 3D. And then this is my roof plan. I still have a 12-inch overhang, 22 galvanized steel deck, and a 10 by 25 section. Nothing has changed from there. As for my plan view, again, not much has changed from the last presentation. However, I still have 12 feet columns, sorry. And my 25-foot long beam spaced at 10 feet with 40-foot long girders spaced at 25 feet. Then as for what I've been doing since our last presentation, I added bracing to my building in RESA 3D. I did this by checking the node deflection in RESA 3D with the limit of story drift from the ASCE 716 manual. And the story drift limit is H over 500. So I got that to be 0.288 inches and added braces until my story drift was less than that. I did this by kind of guessing and checking until it was accurate and tried to add the bracing on the outside of the building to not disrupt any classrooms or laboratories that would be put in. As for my members, the beams and girders have not changed. However, I added the bracing and that is a W8 by 10. And then for my columns, their sizes have gotten bigger since I was able to add in the horizontal loading in RESA 3D rather than just the vertical loading. As for my floor slab, the temperature and shrinkage reinforcement also controlled for my floor slab. So I got a number 3 reinforcement steel bars spaced at 16 inches with a slab height of 2.5 inches spanning 4 feet. And this will be typical throughout the entire building. For my connections, these are also typical throughout. All the connections will be shear connections except for connections with the braces, which will be tension connections. Each of these have been deemed to be a double angle and are drawn above both with a bolt diameter of either 1 or 1.25 inches. These were all checked for rupture in the shear and bolts and the bearing strength. As for my cost estimate, similar to what Emil said, mine has decreased quite a bit as this is just the load-bearing members of my building, kind of just the skeleton of it. It will change once the developer gets it and adds all of the finishes. However, this is the load-bearing aspects of the building, and it also includes design coming out to a little bit less than $500,000. Speaking of cost estimate, I have our entire construction cost estimate at a little bit over $5.1 million with a 15% contingency. This is using various existing values, mainly RS means and the NDOT square foot estimator. For our design cost, we used our work logs and only used the design hours from the work log, not the lecture hours or preparing for the presentation to use this. And we used our position classification and the hourly rate based on the position classification with a 15% contingency to get a total design cost of $73,000, which comes out to a total cost of a little bit less than $5.2 million. For our Envision rating, this is a sustainability rating that was required by us. And here you can see that we got a 54 out of 55. A lot of the aspects of this rating were outside of our scope. and would be more of in the construction realm. So they were not included in this. The only one that was not counted for a point, the 54 part of it, was being built on brown fields or gray fields, which is basically just abandoned land. And we couldn't do that as that's not where our project scope lies, so we didn't really have any control over that. But other than that, it was pretty sustainable as shown by our high score. And that's it. Does anyone have any questions?
Question for John. So the 50% nitrogen removal? Well, I would think that's like a best case scenario, right? Because sometimes the water is not going to be in there long enough. The next storm's going to come through and some of that's going to get pushed out. So it might be a little bit less than 50%. Is there anywhere in your project where you can where you're making that up?
Yeah, so like I said before, so I use it as a very low limit. So in my design, I do have greater than 50% of the water quality volume stored. Let me get back to it 1 second. And then so I believe my water quality volume, I don't have it listed up here. I believe it was around 15,000 cubic feet. So in here I have, or roughly 6,500, 1,600, and then on the last one, 42. So that is above the 50%, but additionally, I did not include any infiltration in that estimate. So looking out here, there's also likely to be infiltration in the infiltration trench through all of the vegetated swales, through these 2 rain gardens, and through the detention basin. So given everything, I assume it's going to be over.
Anyone else?
Transportation, of course. You said, and I saw in your cost estimate,
Mhm,
you included signing
mhm.
and roadway lighting.
Yes.
Which I congratulate you for being the first ever to include that
Yeah, thank you.
in the project. Did you
Help with
actually,
my advisor.
did you actually design the lighting or did you just?
So there is like from City of Valparaiso, they do have like a standard lighting. So if I were to design that, I would just use how they use it. They have different like footage depending on how long the road is and stuff. So I would just use their design and integrate it into my design rather than designing it in my own. So, yeah.
Related to transportation. So you mentioned that the cost went up by about $1 million because of demo.
Oh,
So
yes.
what's included in that demo?
So I know for roadway, it's like the cut to get to grade and all of that, and then like the fill and stuff. And then I know we're demoing 2 houses in order to build the buildings and the parking lot and stuff. We tried to get away with not doing that, but it just like didn't work out. So that's part of the demo also. Any more questions?
Thank you.